Today we're diving into a paper that explores how to improve the reasoning capabilities of large language models, LLMs. The paper, CPL, Critical Planning Step Learning, Boosts LLM Generalization in Reasoning Tasks, proposes a new method called Critical Planning Step Learning, CPL, to enhance LLM's ability to generalize across different reasoning tasks. Let's start with the core problem this paper addresses. What are the limitations of current approaches to improving LLM reasoning?
Current methods for enhancing LLM reasoning often focus on improving performance on specific tasks or domains. For example, training on large datasets of mathematical problems can lead to significant improvements in mathematical reasoning, but these gains don't necessarily translate to other reasoning tasks. This lack of generalization is a major challenge in developing LLMs with robust reasoning abilities.
So, the goal is to develop a method that can improve reasoning across a broader range of tasks. How does CPL address this challenge?
CPL tackles this by focusing on learning effective planning strategies. The idea is that by learning how to break down complex problems into smaller, more manageable steps, LLMs can develop more generalizable reasoning skills. CPL leverages Monte Carlo Tree Search, MCTS, to explore different planning steps and learn preferences for these steps based on the final outcome.
MCTS is a powerful tool for exploring search spaces. Can you elaborate on how it's used in CPL?
MCTS is used to build a plan tree, where each node represents a state in the reasoning process, and each edge represents an action or a reasoning step. The MCTS algorithm iteratively explores this tree, evaluating different plans and assigning values to each state based on the expected future reward. This allows CPL to identify critical planning steps that lead to successful solution. So CPL learns preferences for planning steps based on the final outcome. How does this differ from traditional preference learning approaches?
Traditional preference learning approaches often struggle with complex multi-step reasoning tasks because they lack the ability to capture fine-grained supervision at each step. CPL addresses this by introducing step-level advantage preference optimization, StepAppo, which integrates an advantage estimate for step-level preference pairs obtained via MCTS into the direct preference optimization, DPO, framework.
StepAppo sounds like a significant improvement. Can you explain how it works in more detail?
StepAppo leverages the advantage estimates from MCTS to better understand the relative value of different planning steps. By incorporating these advantage estimates into the DPO loss function, StepAppo allows the model to learn more nuanced preferences between steps, emphasizing critical steps and de-emphasizing erroneous ones. This sounds like a very effective way to learn from the MCTS exploration. What are the key benefits of using StepAppo?
StepAppo enables the model to learn more effectively from the step-level preference data generated by MCTS. This leads to more accurate and robust learning of planning strategies, which in turn improves the model's generalization capabilities across a wider range of reasoning tasks.
The paper mentions that CPL was trained exclusively on GSM8K and MATH datasets. How did it perform on other reasoning tasks?
Despite being trained only on mathematical datasets, CPL demonstrated significant improvements on out-of-domain reasoning benchmarks like ARC-C, BBH, and MMLU-STEM. This suggests that CPL's focus on learning planning strategies leads to more generalizable reasoning abilities.
That's impressive. Can you elaborate on the specific improvements seen on these out-of-domain tasks?
CPL achieved notable gains on ARC-C, BBH, and MMLU-STEM, outperforming baselines and even surpassing the performance of AlphaMath, which was trained on the same datasets using a different approach. This highlights the effectiveness of CPL in enhancing LLM generalization across diverse reasoning tasks.
The paper also mentions a comparison between planning-based learning and solution-based learning. What were the findings of that comparison?
The comparison showed that planning-based learning, as implemented in CPL, outperformed solution-based learning on out-of-domain tasks. This suggests that focusing on learning planning strategies is more beneficial for improving generalization than simply training on correct solutions. So CPL's focus on planning seems to be a key factor in its success. What are the potential limitations of this approach?
One potential limitation is the computational cost associated with MCTS. Exploring the vast search space of planning steps can be computationally expensive, especially for complex reasoning tasks. However, the paper demonstrates that CPL can achieve significant improvements even with a limited number of MCTS simulations.
That's an important point. Are there any other limitations or areas for future research?
Future research could explore ways to further enhance the diversity of planning steps explored by MCTS. This could involve incorporating more sophisticated exploration strategies or using different reward functions to guide the search process. Additionally, investigating the application of CPL to other types of data, such as code, could be a promising direction for future work. To wrap up, can you summarize the key contributions of this paper?
The paper introduces CPL, a novel method for improving LLM reasoning capabilities by focusing on learning effective planning strategies. CPL leverages MCTS to explore diverse planning steps and learn step-level preferences using Step-APO, a new approach that incorporates advantage estimates into the DPO framework. The paper demonstrates that CPL significantly enhances both in-domain and out-of-domain reasoning performance, highlighting its potential for developing more generalizable and robust LLMs.
This was a very insightful discussion on CPL and its implications for LLM reasoning. Thank you for sharing your expertise.